Now we are looking at hard soft acids and bases, which is also called as HSAB concept. So people generally this kind of HSAB concept is mostly referred as like a extension of Lewis acid base theory, or even probably in yesterday's or in our exam time second cycle test, probably I think Hari or some of them were pointing out like how the binding with respect to EDTA, magnesium and so on. Okay, magnesium ion. So how they are interacted with respect to carboxylic acid or nitrogen functionality, hexadentate versus quadradentate, all such kind of things. In order to understand these kind of ionic based interactions, HSAB theory is extensively discussed. Let's look at how the things. Now, before we move on to this topic, I would like to ask few of you to answer this question based on what are the basic acid-base theories. Anyone in the class who can point out what exactly Arrhenius theory talks about? Or I had given two brief points for this, but anyone, some examples like that, would like to comment on what exactly will be the Arrhenius theory talks about, or Bronsted-Lowry theory, or Lewis theory? Anyone in the class? I think someone was answering. Yeah. Okay, so probably you must have read all these things in any case. Acid-base theory is not very young. It's all the way started in the year 1776, where people referred acids as oxides of nitrogen, phosphorus, sulfur, or bases are the ones which react with acid. So these are the examples. And Arrhenius theory talks about hydronium ion formation, like H plus water reacting to give H3O plus. And base is the one which forms hydroxide ion. And a proton donor is referred as Bronsted-Lowry acid, or a proton acceptor is called a base. You can see several examples like this. But there were difficulties in explaining the acidic properties of boron trifluoride and like ions like this silver and so on. So due to which Lewis theory has developed a thorough understanding in recent years based on electron pair acceptor or electron pair donor. You can see that this will be accepting the electrons, and the ammonia or hydroxyl groups will be there to help to give the electrons to the electron deficient compounds. And Ingold, Robinson, Lux Flood, and several systems have come up. Even frontier orbitals of molecular theory, where they simply say the lowest unoccupied molecular orbitals of acceptor is referred as acids, and which donate electrons obviously are donors. You can see that HOMO versus LUMO. So that is the reason I'm telling you it is very extensive update of acid-base theory all the way from 1776 till 1960. Even though many of these compounds have been discussed elaborately. Okay, so this is what, as I told you, Arrhenius, Bronsted-Lowry based on proton acceptor or donor, and Lewis theory, electron deficient compounds or acids, electron rich are called donors. Which essentially brings out to today's topic. What exactly is, how do you rationalize the strength of Lewis acids and bases? Like you all know that sulfuric acid is a strong acid, acetic acid is a weak acid. Even we have done a titration, a strong acid HCl and a weak acid, where will be the endpoints if you react with NaOH. Same way, in Lewis theory, how do you predict the strength? How can you say this ion is more as strong acid as compared to others? Okay, so in order to explain that, you are already aware of electron acceptor versus electron donor as acids versus bases. So the strength of this, depending on the reaction, we need to assess, and it should be a criterion for acid base strength. Okay, especially if we go by Lewis definitions. Again, we need to take into account electronegativity, polarity, steric effects along with resonance structures in order to say the strength, which acid is having strong binding affinity and which is not. So if you look at the observations which are being done like experimentally, you all know that silver bromide or silver chloride precipitation reactions in chlorine estimation, you can see the solubility product. Whereas if you take silver fluoride, it is highly soluble in water. But if you look at down the group, silver fluoride to silver iodide, the solubility product decreases drastically, which means the solubilities of silver halides reduce if you go down the group. Okay, so how do you explain such kind of observations? Okay, because again, it binds. What is a binding strength between silver and fluorine and silver versus iodine? At the same time, many of you are aware of a thiocyanide molecule. So thio means sulfur, cyanide CN. So you have SCN. Okay, so this thiocyanide molecule can have two binding options. If you bring in any metal, okay, like any transition metal, if you bring in, it can either bind to metal by sulfur or with nitrogen. Okay, so what happens if you take mercury ion? It prefers binding with sulfur. If you take zinc, it binds with respect to nitrogen. Okay, how do you explain this? Based on like large and polarizable metal like mercury and small less polarizable metal like zinc. In order to explain all these observations, okay, there is a concept which is called as HSAB concept. H refers to hard, B refers to acid base. So this concept gives a qualitative correlation with respect to Lewis acids and bases, okay, which can be classified as hard and soft. So in 1963, Pearson has proposed this model where hard acids, they combine with hard bases, and soft acids, they combine with soft bases. As simple as that. So this can be a 4-mark question in general. I'm telling, this is not with reference to multiple choice, but in general, HSAB or principle is hard acids combine with hard bases, soft acids combine with soft bases. So this is called HSAB concept or theory. So he is Professor Pearson from like California, like University of California, Santa Barbara. So he has attempted to explain how the affinity with Lewis acids and bases will happen. Okay, so this is the HSAB theory. Again, when I say this statement is neither an explanation or a theory, even though we call it as HSAB concept theory. It is just a guideline with respect to certain set of metals or certain set of ligands, depending on the choice. You can qualitatively predict. Again, no quantification here, only a qualitative prediction of acid-base adducts, how they interact. Okay, again, when I refer hard and soft, it doesn't mean that they are very strong acid. Okay, and soft doesn't mean they are very weak acid. You should see as electron donor, electron acceptor. Now, in last class, very last class of our before the exam, we were talking about Fajan's rule, where we talk about polarization power. So how a cation can destabilize an ion. Again, how the polarizing power is proportional to charge density. Okay, so all these points, polarization power is directly proportional to charge density, and we also talked about polarizability, how an ion can polarize, the extent of polarization, and how easily the cation can polarize. And so essentially, if you look at polarization, we see some distortion of spherically symmetric cloud. So these all topics we have discussed in the last class. Okay, so ionic bond, you are clear, easy charges, separation of charges plus and minus. In polar covalent, there is slight change in the polarity, okay, because of various dipole moments. And in the case of non-polar covalent bonds like chlorine and any of the molecules, there will be no charge development. Yeah? So the term hard-soft distinction is essentially based on this. Okay, so how a molecule or ion can be distorted with the effect of how this cation will interfere the cloud of anion. Okay. So again, how the slightly polar species will interact with other molecules is what we have discussed in the Fajan's rule. So these interactions between hard and soft species are very stronger than one hard and one soft. For example, that is the reason why hard acids react with hard bases. So hard acid, the interaction between hard acid and soft base is not very effective. So only hard interactions or hard soft interactions are dominant. So now let's come to see what exactly is a hard acid. Okay, I will give you some examples where you can really understand how the interaction and all more easily. So how do you differentiate hard versus soft acid? Is hard acid should be small in size and it should have high positive oxidation state, and it should not have any outer electrons that are easily excited to higher state. This is about hard acids, again based on MO theory and Fajan's concepts. Now, what about soft acids? It should be larger in size, exactly opposite of this. It should have low or zero oxidation state. For example, if you have here 6, like chromium 6, as compared to here, it should be mercury or mercury 2. Okay, or it should have easily excitable valence electrons. Okay, so now this is the differentiation between hard and soft acids. Now let's understand it more detailed. So what exactly are hard acids? So you are very well aware that like a Na kind of or like H plus, like alkali and alkaline earth metals. You can see here, do not go by sodium being sodium hydroxide, even though it's a base, we are calling it as an acid. You should look at it as electron acceptor, Na plus. So it likes to form with Cl minus to make a bond. Okay, something like that you need to understand. So all the alkali and alkaline earth metals are good hard acids, and high electropositive with very few electrons like magnesium or even aluminum 3, and transition metals with higher oxidation state, manganese, chromium. Okay, because these are not, they won't polarize the ligands. Okay, because you see that Li, aluminum and all Al3, they can effectively polarize, but already the electrons in this system are deficient, so they won't be able to polarize the ligands, and they do not form complexes. So they prefer to form complexes with these donors, nitrogen, oxygen, fluorine atoms, and they have a high charge density, charge per unit volume, and also their d orbitals will not be involved in pi bonding. Okay? So that is the reason why hard acids react with hard bases. I'll give you examples, then it will be more easier. Similarly, what are soft acids? Here, soft acids, as I told you, compared to hard acids, they are exactly opposite. So you have transition metals with lower oxidation state. So how you get lower oxidation state means the size will be larger and less electropositive, polarizable. So all the three properties are exactly opposite of hard acids. And the d orbitals are available for bonding, pi bonding. Okay, and you can generally see second and third row transition metals will be generally referred as soft acids, and as compared to hard acids, these ligands, these soft acids, they like to pair up with phosphorus, sulfur, chloride, okay, than nitrogen, oxygen, fluorine, you can see here. So that is the reason why soft acids react with soft bases. Okay, now acids, hard and soft are fine. What about bases? Okay, now let's see the examples of both hard acids and soft acids. You can see, look at the examples of hard acids. Small oxygen state is less. Okay, even bismuth, aluminium 3, selenium, gallium, okay, or gallium. All these things, they are hard acid. Again, look at the oxidation state with respect to their place in the periodic table. And you also have some alkyl groups and even iodide based complexes, okay, or hydrogen bonding molecules. And soft acids are exactly low. You can see that all the way from copper, mercury, okay, palladium. All these things are soft, very, very important. Even metal atoms and bulk metals, they can be soft acids. And you can see in the case of borderline, like means borderline, you refer it as like in between hard and soft. They are like compared to Fe3 plus, Fe2 plus, and cobalt 2 plus, and in between like that. Okay, even like benzyl kind of phenyl kind of radicals. Okay, so these are hard, soft, and borderline acids. Okay, so in exam, if they ask you HSAB theory, you need to write HSAB theory, 3 lines, hard acid reacting with hard bases, and vice versa like that. After that, you need to mention what exactly are hard acids, or that table where you can differentiate, and then give 1 or 2 examples for hard acid and 1 soft acid. That's it. No need for borderline cases. If you remember, you can write. If you don't remember also, it's fine. Now, what exactly are hard or soft bases? So these should be ligand molecules, or the electron-rich acids will be supplied with lot of electrons. So how you can get is high electronegativity, obviously, and it should be low polarizability, and how the empty field orbitals may exist at, for example, how the presence of field orbitals, because you are having ligands, so they should be able to donate the electrons to the acids. And soft bases are exactly opposite. They should have low electronegativity and high polarization, and so these are orbitals will be more of low lying rather than the outermost orbitals. Now, if you look at the differences between hard and soft bases, you should be having high electronegativity, because fluorine, oxygen, nitrogen, they are very good electronegative species. So these are the ligands. Of course, they combine with hard acids. And these are less polarizable, means because of the hard acid, the polarization extent of this will be minimal and smaller size. So this is the strength of hard bases. So fluorine is the strongest hard base. Yeah, of course F minus if you look at high electronegativity and so on, and phosphorus. So now this is the starting point for soft base. So soft base, the donor atom should be less electronegative. Again, these both should be opposite, and it should have large size, more polarization because of the cation, and they complex with soft acids. So this is about soft bases. Now let's look at what are all the possible examples. So very good example for hard base is water. You can see two lone pair of electrons and oxygen's electronegativity, hydroxide group. So many of you know that hydroxide is a very good base. Okay, and F minus electronegativity and excess ion. Okay, like that. And amines, ammonia, hydrazine, all such. And soft bases, thiol, okay, and sulfate anion, cyano group, carbon monoxide, okay, benzene. These are all soft bases, and in between them like aniline, pyridine, and so on, those are borderline. Okay, so this again, as I told you, if you look at this very carefully, you might be wondering how you can differentiate as borderline. Why some things are borderline? It is same like spectrochemical series, why they are in borderline, because based on the observations or reactivity of these molecules, okay, or these ions with certain cations, the values are they don't they are in between hard and soft combinations. That is the reason why we have a borderline case, both in hard acids and in the base both. Now, so this finally to give few concluding or few more points before we close the class. If you look at the periodic table, so these are the hard acids based on the points what we have discussed, the oxidation state, charge, and so on. And the orange ones are hard acids, and this orange one here are hard bases. But just have a look. Even nitrogen with what it has bonded, like alkyl groups, they are called as borderline. Okay, whereas ammonia and all are hard base, but some part you can see there is a borderline case, and we have borderline acids also based on this. You can see yellow highlight like iron, cobalt, nickel, and so on, including zinc, and soft combinations of acids, mercury, cadmium, okay, and soft bases like phosphorus, arsenic, selenium, bromine also, and at the same time iodine. Okay, and you also have here soft acids like silver and so on, and borderline cases you can see, because it is, you see that there is a change in the periodicity. So finally the take home message is hard acid has a very strong interaction with hard base. Soft acid has a very strong interaction in soft base, means only this combination will be good. If you combine hard acid and soft base, there is no interaction, or the interaction is very weak. But if you combine soft acid and soft base, the interaction is good. Okay, so this is the importance of the, like, the take home message which you should be remembering based on looking at the probable list of elements. Even though it looks very like dynamic or like this, like so many examples, but if you look and understand, it's very straightforward. Okay. Now let's go back to what we have started in the class. how do you differentiate in properties of hard and soft acids is by looking at electronegativity. If the electronegativity values are between this, you call it as hard acids. If it is high, hard base, ionic radius lower than 90, okay, and for hard bases it is 120. If it is higher, above 90, then you call soft acids. And of course, soft bases, they should have larger size. So again, based on ionic charges, you may finally say how the acids and bases can be classified. Yeah. Again, borderline species we cannot pinpoint here because they should be in between these values. Yeah. Otherwise, it is easy for them to classify, but we don't generally won't classify them between hard and soft. Okay. Now, as I told you, being the beginning of the class, how do you know that sulfur is binding to mercury? Because mercury 2 plus is a soft acid and thiocyanide is a soft base, so it is a soft combination. So hard acid, soft acid and soft base combination, whereas zinc and cyanide like NCS will form a hard combination. Okay, that is the reason why zinc react with nitrogen, mercury react with sulfur. Same way here you can see, like iron thiocyanide complexes, you can see that nitrogen bonding with iron, whereas if you replace gold, it binds with sulfur. Okay, I think many of you are aware that gold, cadmium, or mercury, they like sulfur so much. So somehow they interact with sulfur rather than even some other metals are there because of soft or hard combination. Yeah. So this is one such application where we started, and even we told why silver halogen solubility reduces. Okay, so a complex will be more stable if both are hard or soft, depending on that. So silver iodide is very stable, silver fluoride is not. That is the reason we see a very weak solubility of silver iodide complex, because you have a reaction between soft acid and a soft base. It's a very stable complex. But if you have fluoride, which is a hard base, you already know that if you react with this, very unstable. So due to which the solubility is high, very less in the case of silver iodide. So what we started, we ended up saying this is the basis for the solubility. Okay. Now, so all this material I had taken mostly from these handouts. Okay, your NPTEL lectures, and also the chemistry 3 book, which is a very, very important book and a very interesting book as well. So any doubts you can clarify now. Is there any doubt on like acid-base theory or any or such anything? Or you want to go through the handout because you must have been more looking at the examples and based on that. Yeah. You want the handout so that you can go through that, and if any doubts are there, you can ask me. So is there any doubt to anyone?
No, sir.
Okay. So as I told you, I will post the material today and have a look, and if there are any clarifications or any doubt after that, you can go through it. But just remember, this hard and soft acid base concept is an outcome of like polarization and like how the reactivity between mercury and sulfur or the solubility issues can be examined, even though we are very sure that if you move down the group, the solubility reduces, but how the you can explain based on soft acid and soft base combinations. They are very stable as compared to soft acid and a hard base or something like that. It's only thing is you need to read the examples, and also you can also look at like molecular orbital point of view. Okay, all the time remember, whenever we call an acid, it is how the acid electron deficient will be ready to accept electrons from a base. So instead of base, people call here as ligands because they are filled with electrons even from lone pair or because of their charge. Okay, it can be minus hydroxyl or all the way till P3 minus and so on. Okay, so if there is no doubt, we may, yeah, I will stop the recording and